Now that you have been introduced to the concept of correlational analysis and you have some understanding of positive where the two variables run together, negative where one goes up, the other one goes down, and you have some idea of a strong versus a weak relationship, I want to examine the way that we express strong and weak and positive and negative with a variable. And what we're going to look at is called the Pearson R. And R stands for the correlation coefficient. That's going to be a number, which when we look at it, we will be able to tell whether it's positive or negative and be able to identify whether it is weak or strong. Bivariate correlation coefficient is a value that expresses the strength of the correlation between two variables. The Pearson product moment correlation coefficient, which is represented by the little letter small r, is one way of expressing the strength of the correlation between two variables. And we will be able to look at the r value and we will know whether it is positive or negative. We will be able to tell whether it is weak or strong or in the middle, a moderate correlation. Some points to remember. The Pearson R is founded upon the assumption that the two variables are normally distributed. Now, how do you determine normality? Well, remember, you take the variable, you run its descriptives, and you ask to see the skewness and kurtosis. And if the skewness and kurtosis values are in between -3 and 3, then it is approximately normally distributed. If the variables are not normally distributed, other measures are required. And what we do in that case is we run what's called a non-parametric correlation coefficient. Non-parametric simply means not normally distributed. But the Pearson R assumes that the variables are normally distributed. So we will look at skewness and kurtosis as part of the protocol in order to determine if the variables are approximately normally distributed or not. Now, the Pearson product moment correlation is a value between -1 and 1. The number 1 means we have a 100% positive correlation. They are traveling the same direction, and they are absolutely 100% acting together. -1 is a negative 100% correlation, which means they have a negative as one goes up, the other one goes down, but it is 100%. And everything then in correlation falls between -1 and 1. And generally we see it as a value of 2 decimal places. And 0 means there is absolutely no correlation. So the Pearson product moment correlation, or the Pearson coefficient R, is generally expressed as 2 decimals. The Pearson moment correlation has what we consider a strong correlation. If the strong correlation falls between 0.50 and 1, or between -0.5 and -1, then it is said to be strong. That means that we could say R squared is greater than 0.25. A lot of times we talk about the Pearson correlation in terms of R squared because the R squared does away with the sign. So if it falls in the value between -1 and -0.50 and 0.5 and 1, then it is a strong correlation. A correlation can also be moderate. Moderate falls between -0.50 and -0.30 and 0.30 and 0.50. So it falls in this value range. We would call it correlation. And if it falls between -0.30 and 0.30, then we say it is weak to no correlation. Now, we express this in values of R squared. R squared is greater than 0.25, it's strong. If R squared is between 0.25 and 0.09, we can say it's moderate. And if R squared is less than 0.09, we can say it is weak to no, or weak to none as far as the strength of the correlation. So we look at the value of this correlation using the Pearson product moment R coefficient. The Pearson product moment R coefficient assumes that the variables are normally distributed, which means that we have to look at skewness and kurtosis to establish that they're approximately normal. And then once we get that, if it is positive, it's a positive correlation. If it comes as a negative, it's a negative correlation. And then we can value the strength of the correlation using the scales that were represented. So we can look at moderate, strong, moderate, or weak to none as far as correlation. Some important points to remember about correlation. Some correlations are meaningless. I always find it hilarious when they've got the correlation between the full moon and emergency room visits at the hospital. Well, I know that the werewolves are out and they're hurting people and the moon's pulling up on our brain and all these things are going on. But just because we have a correlation does not mean that we have a cause and effect. Yes, there is a correlation, but is cause and effect in that case real? I don't know. You know, just because the correlation's there doesn't mean that it's real. R is a measure of a linear relationship. That means that a linear relationship, they're traveling in a line, and you will understand more about that as we get into the next section. And a curved relationship may show or may not be effective, okay? R does not say anything about cause and effect. Just because we have a correlation between shoe sizes and number of people that eat peanut butter doesn't mean that if your shoe size is a certain thing, that means you eat peanut butter. Or if you eat peanut butter, it means your feet big. R and correlation coefficient does not establish cause and effect. R simply states that the variables are related. They travel together or they travel against each other. Remember, if they travel together, they're positive, or if they travel against each other, they're negative. The protocols for the Pearson R require this. Requires normality of the variables and is the foundation of linear, the Pearson R is the foundation of linear in relationships, and it does not indicate cause and effect. The thing that you really look at as you do conduct a correlational analysis, the first thing you would establish is if these variables fall into the Pearson R and by being approximately normally distributed. And to do that again, you look at skewness and kurtosis. If they are not normally distributed, then there are other correlational values like the Tyndall's tau and others that don't require normality. They are non-parametric. Again, non-parametric means that you do not have normality. Now, don't panic. You've got this. This is not hard at all. All you have to learn to do now is to put your two variables in SPSS and run a correlational analysis. And remember, you're comparing two variables at a time. That's all you can compare. Two at a time, bivariant correlational analysis. So don't panic. You've got this. You put it in SPSS, use the menus correctly, punch the button, and away you go. Look forward to sharing with you how you actually do that.